This is our next problem for working out reaction forces. We have a UDL, or uniformly distributed load, spread over the length of a beam, which is 3 meters long, a fixed support on the left and a roller support on the right. First move will be to draw a freed body diagram of our beam, replacing the fixed support with 2 forces, the roller support with 1 force. Labelling, label the left hand side A and the right hand side B. So for the forces I can put in VA and HA and VB. Draw in the UDL and label it. In this case it's 20 kilonewtons per meter. With our freed body diagram, we can apply our 3 equations for equilibrium. All the forces in the x direction must add up to give you 0. All the forces in the y direction must add up to give you 0. And all the moments about any point must add up to give you 0. Remember the sign convention. Up is positive, down is negative, to the right is positive, to the left is negative, clockwise moments positive, anti-clockwise moments are negative. Applying the first of our equilibrium equations, we have one horizontal force that's going to the right, therefore it's positive. That's the only horizontal force we have for equilibrium. It must add up to give you 0, therefore your HA takes a value of 0. That's your first reaction force worked out. Apply the next equation for equilibrium. All the forces in the y direction add up to give you 0. We have here essentially 3 forces. We have our reaction VA going upwards, positive, VB positive, going upwards, and then we have the weight of the UDL acting downwards. In this case our beam is 3 meters long, so the entire weight of the UDL acting downwards, negative, will be 20 times 3. 2 forces up, 1 force or UDL acting downwards, it's negative. For equilibrium they must all add up to give you 0. VA plus VB minus 60 equals 0, or VA plus VB equals 60 kilonewtons. If we can work out one of the reaction forces, we can easily work out the other one. Now applying the third equation for equilibrium. All the moments about a point must add up to give you 0. Remember, moments are a force by a distance, and we must specify which point we're taking moments about. In this case I'm going to take moments about the first support on the left hand side. That's labelled point A, a little bent arrow over the top to denote the shorthand version of taking moments about point A. And we have, go back to our free body diagram, HA and VA are applied at point A. Their offset distance is 0, so don't produce a moment. What does produce a moment is the UDL and the force VB. Now, when dealing with the UDL, what we do is we take the entire weight of the UDL, in this case 20 times 3, which is going to be 60 kilonewtons, and we put it in the middle of the UDL. So effectively, when we're doing moments, we replace the UDL with a point load of 60 kilonewtons, and that would be at a distance of, in this case, 1.5 meters across from point A. Now, when we're doing moments, it will be 60 times 1.5. The other moment, or the other force that produces a moment, is the force VB, and it's going to be 3 meters across from point A. These are the only two forces that produce a moment. For equilibrium, they must add up to give you 0. Now we'll consider the direction, clockwise or anti-clockwise moments. Remember, clockwise moments are positive, anti-clockwise moments are negative. Now going back to our free body diagram, consider each of the forces. So we're considering the 60 kilonewton load concentrated down and how the moment would work for that. So your force is on a piece of string. You hold the string at point A and you allow the force to freely rotate around that point, and it will want to rotate around in a clockwise direction, therefore is a positive moment. Doing the same for the reaction VB. Hold, it's considered a force on a piece of string. You're holding the string at point A. The force is allowed to freely rotate around point A, and it would want to go around in an anti-clockwise direction, therefore would be a negative moment. Then we can work this out. 60 times 1.5 gives you 90, minus 3 VB equals 0. 90 is equal to 3 VB, taking that to the other side. Then dividing through by 3 gives you VB, and that works out to be 30 kilonewtons. Then applying the equation that we worked out earlier, VA plus VB equals 60. We can write the equation down, do our substitution in for VB, and rearrange the formula, taking the 30 to the other side. Your VA also works out to be 30 kilonewtons. Answers in this case are HA is 0, our VA is 30 kilonewtons, and our VB is also 30 kilonewtons.